The purpose of this video clip is to demonstrate that without air resistance, without air, the acceleration of gravity on all objects near the surface of the Earth is the same, and that acceleration is 9.8 meters per second squared, or in this class, and the best approximation is 10 meters per second squared. First, let's quickly review, though, what the equations are for constant acceleration and near the Earth's surface, and how that affects an ideal body where you don't have air resistance. And then we'll look at air resistance qualitatively, and then do a demonstration showing that when you remove the air, two objects, a penny and a feather, fall at the same rate. Okay, now for constant acceleration, we developed several equations. One of those was the speed of an object, or velocity if we're looking at the vector, after some time is equal to the acceleration, g in our case, times the amount of time that's passed, plus how fast we were going initially. Okay, we also developed an equation for the change in the position, or in our case, y, since we're looking at vertical change. The change in position in the y direction is equal to 1/2 times that acceleration of gravity, g, times the time squared, plus the initial velocity, v1, times the time. Okay, now, if initially we start out at 0, which is in this problem here what we're doing, and in many problems here, v1 is equal to 0, in that case, this is 0, and this is 0. And that simplifies both of these equations. So we have delta y is equal to 1/2 gt squared, and then we have our velocity equation, v2 is equal to g times t. Two simple equations. Now, let's just put in some numbers here, and in this little chart down here, where we'll put time here, and our positions here. So at 0 seconds, 1 second, 2 seconds, 3 seconds, and so on. We'll put our position in here, each one of these, and our velocity. Okay, in the first, at 0, we start out at 0, and our velocity is 0. Okay, then at 1 second, when we start out at 0 velocity, we'll be at 5 meters, and our velocity will be 10 meters per second. At 2 seconds, we'll be down 20 meters, and our speed will be 20 meters per second. And at 3 seconds, we'll be down 45 meters, and we'll be going 30 meters per second. Okay, we could keep on going with that, but that's enough. Okay, so let's come over here now to this graph here, and so after 1 second, our ball has fallen to here. It's dropped 5 meters. After 2 seconds, it's dropped to here, and it's going at a speed of equal to 20 meters per second. And here it's 10 meters per second. And if we wait 3 seconds, and if we're up high enough, after 3 seconds, this thing will be going it'll be down 45 meters, and it'll be going 30 meters per second. And that's pretty darn fast. Okay. Now if we take a larger object, what we're arguing here, a much larger ball here, and we drop these two at the same time, we'll see our larger one is in the same position at the same time. Both of these fall at the same rate. However, that's not exactly what we see in the real world. Generally what we see is heavier objects hit before lighter objects. And we all know what happens when we drop a piece of paper and a heavy ball like this. The ball hits first, the piece of paper flutters down. Now, if I take this piece of paper and I crumple it up, and I repeat this experiment, they fall at about the same rate. Why? Well, you'd all basically say it's air resistance. And yeah, that's what it is. However, let's look at that a little bit more carefully. What I have here is a couple of diagrams here that'll just quickly describe air resistance in a qualitative way. I've got the paper sheet here flattened out and the paper sheet crumpled up. Okay, and then I've drawn a couple of arrows here, vectors, force vectors, and we'll get to that later, what these are in more detail. But we can see the gravity pulling on this piece of paper here. The length of this arrow is the same as this, and the force down is equal. This is equal to that. However, the air resistance of the big sheet of paper is greater in the open sheet than it is when it's crumpled up. Smaller arrow, smaller force. The greater upward force here causes this paper to drift down more slowly, and this one falls more rapidly. Air resistance simply results from pushing the air out of the way. You've got to push more air out of the way here than you do here. But that doesn't explain what happens when you've got two objects the same size, and one has a big mass or a big weight, and the other has a little one. I was arguing that these are going to fall at the same rate. Now, we'll talk about the physics as to why this happens later. Today we're just looking at why this actually occurs, or a thought experiment that explains why this happens. Galileo's thought experiment went something like this. You take three objects, books in our case, 1, 2, and 3, and they're all identical, and you drop them, okay? Now, I think we all would agree that they're all going to fall at the same rate, and they're going to all hit at the same time. So their accelerations will all be equal. Then he says, well, let's see, let's take 1 and 2, and let's hook them together with a rope. And let's do the same experiment again, drop everything, and now, okay, we're all going to pretty much agree that, by golly, they're going to all hit the same, because really nothing much has changed. There's a little bit of air resistance due to that rope, but they're all going to hit at the same time. Now, he argues, though, that this right here is actually an object that's twice as massive as this one, but they still fall at the same rate. And to make that point, he says, okay, let's shorten up the rope so short that they're touching and actually hooked together, and do the experiment again. They hit at the same time. This thought experiment is what Galileo used to demonstrate that it didn't matter what the mass was if you got rid of air resistance. All the objects would fall with the same acceleration. This experiment, thought experiment, was simple and yet very profound. Okay, all this, Galileo's beautiful thought experiment, argues that all things would fall the same without air resistance. Well, how do we get rid of the air? Well, we're going to demonstrate that now. I'm going to do this with a feather and a pen. There's a feather and a penny. There's the penny. Okay, what I'm going to do is there's a valve on the end. This is a glass tube that's sealed, and I've got this valve open, so there's plenty of air in this tube right now. And I think you guys can see this here. I'm going to take this tube and I'm going to flip it over and watch the penny and the feather. See the feather flutter down. Okay. Now, let's take the air out of this thing, and I'll hook it up to my vacuum pump. Okay. I'm going to turn my vacuum pump on here and pull a vacuum. Put this on my tube. Pull it down here, keep it pumping. was here. Go. Close off this valve here. And shut the pump down. And then we'll disconnect this tube. Okay, now here's our tube here. We've pulled most of the air out of it, and now let's see what happens. You can see the feather and the penny in the bottom there. Move up a little bit closer. You see they hit just about at the same time. Feather and the penny. You pull out most of the air, and they fall at the same rate. Galileo was right.